CRT-Power is a program to perform power analysis for cluster randomized and multi-site trials. This video highlights the program's features. These include setting the number of levels, setting the level of randomization, specifying the ICC and the variance of effects, entering data for covariates, entering data for costs, finding the optimal design, finding the minimum detectable effect size, generating graphs for export to Word or PowerPoint, displaying this information in tables, generating an executive summary and detailed reports, moving from the optimal design program to this one, and more. This video runs about 15 minutes, but you can use the arrows to move between sections. Case study. Let's assume that we're planning a study where the outcome is the SAT score. We will be comparing scores for treated versus control. We are going to be looking at students, within classes, within schools, within districts. Initially, the program displays two levels. I will add a third and a fourth. And then I will name the levels: students, classes, schools, districts. We can randomize at any level. If I randomize districts, schools, classes, and students are nested within districts. If I randomize schools, districts are blocked, while classes and students are nested within schools. And so on. For this example, I will randomize districts. We need to specify the interclass correlation, or ICC, for classes, schools, and districts. I have two options here. I can specify the ICC. In that case, the program will show me the corresponding span of means. Alternatively, I can specify the span of means. In that case, the program will show me the corresponding ICC. The ICC for districts is 0.02. If the grand mean for the control group is 500, the district means will range from 472 to 528. The ICC for schools is 0.05. In a district where the mean is 500, the school means will range from 455 to 545. The ICC for classes is 0.12. In a school where the mean is 500, the class means will range from 431 to 569. And finally, in a class where the mean is 500, the student scores will range from 320 to 680. This feature, the ability to enter the ICC and see the corresponding span, is important for two reasons. First, it allows us to ensure that the values we entered for the ICC are appropriate. Second, it provides a mechanism to communicate this information as part of a report or grant application. The ICC deals with the variance of scores. When some level of the study is blocked rather than randomized, we also need to provide the variance of effects at that level. Suppose that districts are blocked. We need to specify the variance of effects across districts. Let's set the mean effect size to 0.50. This works the same way as the ICC. I can enter the variance of effects, tau squared. In that case, the program will show the corresponding span of effects. Alternatively, I can specify the span of effects. In that case, the program will show the corresponding value of tau squared. If the overall mean is 0.50, the mean effect size in any given district will range from 0.40 to 0.60. You can enter any number of covariates for each level of the design. These covariates will reduce the error term, which can substantially increase the power. In this case, the mean SAT for the prior year may serve as the covariate. We expect that to account for around 30% of the variance of district means, 40% of the variance of school means within a district, 20% of the variance of class means within a school, and 30% of the variance of student scores within a class. Initially, the statistical model for all levels is set to random effects, but some can be changed to fixed effects. I can set the cost for every unit. Each district will cost $4,000. Each school will cost $3,000. Each class will cost $500, and each student will cost $50. We set the effect size. If the outcome is continuous, the effect size will be the standardized mean difference, D. There are two versions of D, and we can use either one. The first is the difference in means standardized by the standard deviation within clusters, which we call D within. The second is the difference in means standardized by the standard deviation across the entire sample, which we call D total. If the outcome is dichotomous, the effect size will be either the odds ratio or the risk difference. At the moment, we're working with a continuous outcome, and we are using the standardized mean difference D total. Earlier, we set this value to 0.50. I will set the value of alpha to 0.05 and specify that this is two-tailed. Initially, we are looking at 2 units at each level, so power is only around 12%. Let's assume we want a sample size that will yield power of 80%. We can ask the program to give us the most cost-effective design, which we call the optimal design. The program tells me that this would be 5 districts, 2 schools per district, 3 classes per school, and 8 students per class. This will give us power of 80% for around $150,000. I can paste these numbers into the main screen. I want to point out one important feature of this optimal design function. The program told us that we should enroll 3 classes per condition per school. Suppose that, for administrative reasons, we want to enroll only 2 classes per condition per school. We can set the number of classes at 2 per condition. The program will honor that constraint and find the optimal numbers for the other levels. That turns out to be 6 districts, 2 schools per district, 2 classes per school, and 7 students per class. When we use the optimal design wizard, we specify the effect size and the desired power, and we ask the program to give us the sample size. We can also reverse the process. We can give the program the sample size and desired power, and ask it to give us the smallest effect size that we can detect with that level of power. This effect size is called the minimum detectable effect size, or MDES. We know that with 5 districts per condition, we have 80% power to detect an effect size of 0.50. Suppose we enroll 10 districts rather than 5. What would be the minimum effect size we could detect then? The program tells me that if we increased the number of districts to 10 per condition, we would have 80% power to detect an effect size of 0.317. The program will generate 2 reports. The first is an executive summary. One section reads, "The study will employ a 4-level hierarchical design, using students within classes, within schools, within districts. Districts are randomized, schools are nested within districts, classes are nested within schools, and students are nested within classes." The report incorporates the table shown here. The section on power reads, "Given the design, sample size, assumptions, and criteria outlined here, the study will have power of 81.1% to yield a statistically significant result." This is followed by a section on costs. And finally, there is a disclaimer advising the reader to consult a statistician. The second report incorporates the executive summary, but also includes an explanation of each item. For example, it includes this table. The section at the left gives us the span of effects within each cluster. The section at the right gives us the span of effects across all clusters. Student scores within a single class would range from 320 to 680. But student scores across the entire sample would range from 300 to 700. We can use this to ensure that our numbers are plausible and to communicate this information to others. This report also includes sections that explain all details of the computations. The program will create a graph. In this graph, the x-axis displays the number of districts per condition. The program can plot both power and cost, so we can use this plot to find the best balance between the two. The plot shows that increasing the number of districts has a substantial impact on power in this range, but only a trivial impact beyond that. By contrast, the increase in cost is linear, so the best balance would probably be somewhere in this range. We might elect to focus on these 2 points. With 5 districts, power would be 81% at a cost of $154,000. With 6 districts, power would increase from 81% to 90%, but the cost would increase to $185,000. We can also include a second factor in the plot. Now, we can look at power as a function of number of districts and effect size. With 5 districts, power would be here for an effect size of 0.6, here for an effect size of 0.5, and here for an effect size of 0.4. This box shows the details for any factors that vary in the plot. We can also add a footer with all the factors that are constant. I can plot this graph using almost any element for the x-axis. This plot shows power as a function of the effect size for 5, 6, or 7 districts per condition. The graph can be exported to PowerPoint or Word. We can also display this information in a table. Let's go back to the main screen and have a quick look at some other features. We can set a different cost for treated versus control units, and we can set a different sample size for treated versus control units. The program has two help systems. The first help system will provide information for any element on the screen. For example, I can click on ICC. The program opens this frame. This button displays an overview of the ICCs. This one provides the formulas for computing ICCs, and so on. There is also a second help system. This one provides a step-by-step guide for computing power. How to set the effect size, alpha and tails, the study design, the number of units at each level, the ICC, tau squared, covariates, statistical model, and costs, how to manipulate the sample size, how to find the optimal design, how to create a report, how to find the MDES, perform a sensitivity analysis, make a graph, save scenarios, and save the file. As you work through the design process, you will probably try a number of different scenarios. You can save each scenario to a table. For example, you might consider randomizing districts, and you can save that. Then, you might consider randomizing schools, and you can save that. You might try different values for the number of classes, or the costs, or anything else, and save that to this table. You can even annotate each scenario. When you save the file, all scenarios are saved with it, and the next time you open the file, you can retrieve any of them with one click. Some of you may be using a program called Optimal Design. Optimal Design and CRT-Power use the same algorithms, but different nomenclature. The concordance between the two programs is detailed in this paper. Additionally, our program offers an easy way to move from that program to ours. Select any design using the Optimal Design nomenclature. The program will open the corresponding design in CRT-Power. For continuous outcomes, Optimal Design has a design called Person Randomized Trials, Multi-Site, or Blocked Trials. Click that, and CRT-Power creates the same design here. And so on for the other designs for continuous data. For binary outcomes, Optimal Design has a design called Cluster Randomized Trials with person-level outcomes. Cluster Randomized Trials. Treatment at Level 2. Click that, and CRT-Power creates the same design here. And so on for the other designs for binary data. CRT-Power offers additional designs as well. There is a manual provided for those who want to learn more about power for these kinds of studies. The manual explains the theory behind power for CRTs and the formulas used by the software. It includes numerous examples of case studies. It also includes details on the concordance between the nomenclature used by Optimal Design versus that used by CRT-Power. A word about our company. We have been developing software for meta-analysis and power analysis since 1985, and our software is used by tens of thousands of researchers across 67 countries. Our original power analysis program is called Power and Precision. This software was also licensed by SPSS and then IBM and distributed under the name Sample Power, which is their trademark. Our meta-analysis software is called Comprehensive Meta-Analysis. The primary developers of CRT-Power are Larry Hedges and Michael Borenstein. We would also like to acknowledge the help provided by Mark Lipsey, Steve Rodenbush, Jessica Spybrook, and Chris Rhodes. Development of this program was funded by the NIH, the National Institutes of Health. The website for this program is CRT-Power.com. There you can download the manual, order a license for the program, and submit any questions. Thanks for your attention.